Hello everyone, welcome to MarinEngBase again. So today my topic is AC and DC motors. Here I'm going to discuss from the starting from the basics, and I will dig into the very deep concepts and the theories behind the motors. Let's say we'll start from the construction of the motors and the group of the motors, and then the basic working principle of the motors. Thereafter we'll move to the torque characteristics, how the reactance and the resistance will impact on the torque characteristics or power factor improvements, these things, and then the starting theories and how we are going to reduce the starting current, starting torque, how we can improve. So these things and the motor protections, starters. So these things will be discussed. So first, let's have a look in onto these types of motors. Types of motors we can see in the industry as AC motors and DC motors. AC motors again we can group into synchronous and synchronous. The synchronous means your rotor is driving at the same speed as its stator rotating magnetic field speed. Whereas the asynchronous motors, their rotor will have a slip and they will be little lesser, drive at a lesser speed than its rotating magnetic field of the stator. So this is asynchronous motors we can see as a squirrel cage. That is the most wide use application in the industry, squirrel cage motors, because they are very simple. So we will have a look. And then the wound rotor. Wound rotor means your rotor, the rotating part is contained with the winding. Then the DC motors. DC motors, again, we can divide it separately excited. That means to create the magnetism that you have to give some separate power. And the other group is self-excited, where the field or the magnetic field is created through the same supply. So to get done that, you may have a shunt winding, that means parallel connection of these two winding, or the series winding wound, or the combination of these two, shunt and series. So we call it compound winding. So apart from that, in the industry we can find the other AC motor types like normal induction motor, synchronous motor, commutator motor, more or less that you can find commutator motor in your handrails, grinder machines, or these are with the commutator motor. And wound rotor motors, squirrel cage motors. DC motors, again, shunt, series, permanent DC motors, permanent magnet DC motors, compound motors, then the special motors like electronic, the stepper motors, the governor control and these things, the brushless motors, motor, then the universal motors. Okay, so then we'll move to first to discuss about AC induction as synchronous motors. Three-phase induction motor. Oh, now you can see this is cross section or stripped view of the motor of AC motor. And if you closely look, you can see this part which remains in middle, that is your rotor. That is the part which rotating, and it rests on two bearings. These two bearings are mounted on the end covers, and there is a fan, cooling fan connected to the same shaft, so it will cool down your motor while it's operating. And these pins on the enclosure will help to cool down, increase the surface area, and increase the surface area to enable more heat transfer. And also you can see some fins inside this rotor, built-in vanes, some kind of. So these are also cooling fans. Then, so this is the rotor. We cannot see here apparently any winding on this rotor. So this is not a wound rotor. This is just a squirrel cage we call. So in soon we will going to have a discussion of this kind of rotor. Then you have your motor enclosure, and this enclosure contains the stator winding. So this is the stator winding. This stator winding, the terminal is going to terminal blocks. This winding wires are going to terminal blocks, where that you give the power to start or run the motor. And this drive shaft, this side we call it as the drive end or D end, the other side is non-drive. Normally, the cooling fan is connected at the non-drive end. The load is coupled to the drive end. Right. So then for basic construction, we will have a look on this strip view. So there are two main components, the stator and the rotor. The stator is the one which contains the coil, sets of coil, which creates the rotating magnetic field, and then the rotor, which pass through the stator, and there will be a clearance between the stator and the rotor, which allows this rotor to freely rotate, and the bearings will install on the end covers. Right. So first we'll look what is stator. So stator is something similar to this arrangement. Here, this is a three-phase stator. That means you have this blue, red, and green three-phase or three supply. So three-phase supply, so that means AC supply, blue, green, and red. And if you consider this blue line, you can see it is going to a winding in this end, and then opposite to that, it's flowing into another. It's making another winding. We call it a pole. Here is one pole, and it's creating another pole, and it's returned back. So the same way, the red one, it creates a one pole, and it is going to the other side, opposite side, and it comes out. Same way the green one. So these three phases creating 6 poles in this arrangement. So these are the windings actually, copper windings. This is a steel core. Inside this steel core that we have embedded a few windings, arranging 3 phases. Normally these 3 phases are arranged in 120 electrical with an electrical angle. So to have a proper smooth operation, to enable the proper smooth operation. Then now if you remember in this drawing, there are 6 wires, 1, 2, 3, 4, 5, 6. These 6 wires you will take into the terminal box. Then we can see, so this is the terminal box. There are 6 wires, 1, 2, 3, 4, 5, 6. These are the wires that green, red, and blue. So there are 2 drawings provided here, red, blue, green, this one and this one. This configuration we call star configuration, whereas this one we call delta configuration. So in this case, to form a star winding, if this red winding, the 2 ends are U1 and U2. For green, it is V1 and V2. For blue, if it is W1 and W2. If you connect U2, V2, W2 together, so it will create a common point here. And the other ends that you can take out, 3 wire will come out. So you can give 3-phase supply to this one. So then this motor is considered as a star driven motor. So the cable connection for that configuration is like that. You can see V2, U2, W2, they are connected with this strip. And this side you are going to give your supply. So this motor is running as a star, like in this top configuration. If you want to run this motor as a delta, suppose in this case, so then you have to remove this common strip, contact strip. Then you have to connect in this way, arrange like this. So to connect W2, U1, U2 to V1, V2 to W1. You can see W2, U1, U2, V1, W1. So easily you can swap motor stator connection between star or delta. You can do this one via a contactor set or by simply permanently run with these connecting pieces. And what is the purpose of having this star and delta? Let's see. In star configuration, we can see through one coil, one phase, the voltage is only 240. 240, because this 440 line voltage will divide it between these windings. So then this 240 volts only apply in one phase. This is now in delta connection, your line voltage 415 and it is directly applying on these two windings. As this is a parallel connection, the voltage is applying on both the windings, 415 full voltage. Here it's a series arrangement, you can see between this line. So the voltage is dropped. So 240, 240. Now, wherever you have lesser voltage, you will have a lesser current. It can draw only lesser current. Same like in your house, if your water tank, if it is half filled, then if you open your tap, your flow is less. So if you want to have higher flow, then you have to fill your water tank full. Then you will have a much higher flow. Same scenario. Let's equalize this. Let's think in that way. This voltage is similar to your water tank. The energy stored in your water tank. In that case, if you want the current flow, we will think in this way that the water which is coming out from your tap is the current. So if you have low water in the tank, you will have less flow. So in the same way, if you have low voltage, then your current flow is less. So we know that normally when starting a motor, it draws its maximum current, because as the motor is stationary, your rotor is stationary, to getting start to overcome its inertia, it's draw highest current. So to minimize that highest current, you can use star connection, because with the availability of low voltage, it cannot draw the current as much as it needs. Once the motor has started, obviously it will create low torque, because the voltage and current both are less. So the power will be ultimate, it will be less. Even though that, but you will have less current for starting. So that is good for your cabling and other protection. For you, your other systems will not get interrupt with the power surge and these things. So normally the large motors, they are started on star configuration, run for few seconds. Once its inertia overcome, then it change over to delta. You will have a separate starting mechanism for that. Right. Next, that is about your stator. Now we'll move to the rotor. The rotors, majorly there are two types of rotors. The first one, you can see this is a squirrel cage rotor, because that is the shape is almost similar to a squirrel cage. You cannot see any winding here. These are just some kind of conductor bars, aluminium or copper, and they are connected at their ends with a end ring, and creating a loop. We will discuss later. But in wound rotor, you have more complex arrangement. You have winding, same like your stator, you have some winding, copper winding inside your rotor. And these windings, the ends are brings to slip ring arrangement. And with the slip ring arrangement, these are normally connected to external resistor bank. This is for compensating the torque requirements and to have higher torques and some other application. But widely we are using the squirrel cage because they have less complexity, less maintenance. Right. This is a squirrel cage motor basic appearance. So suppose this is the rotor and the outer one is the stator winding, and this is the view. The shaft is there, the rotor core is there. It almost looks like a squirrel cage. Right. Normally, these copper conductors which are connected, these two end rings are not parallel. Mainly, they are at an inclined angle. This is to make this smooth torque transition while it's rotating. So these motors are widely used because they are very robust, because there is no any slip ring arrangement brushes. So you have very less maintenance. So this is the basic arrangement of your squirrel cage rotor. This is your wound rotor motor arrangement. This is a diagram of a wound rotor. So this is your rotor. This rotor, it has three windings and brought into your slip rings, and with the use of brushes, it's taken out to a external resistor bank. So this is to improve its starting torque characteristic. Later we will reveal why it is required that increase the rotor resistance, how it affects the motor torque characteristics. Right. This is again the wound rotor construction, how it appears. Normally at starting the max resistance is applied, so then you will have a higher torque. Then once it's reached its speed, this resistor bank omit. Let's end this session after discussing the basic operation of a three-phase induction motor. So to explain the basic working principle, we can have a look in Fleming's left-hand rule. So if you have a current flow 90-degree on another plane to your magnetic field, then there will be a force generating in this conductor, current carrying conductor, perpendicular to both magnetic field and the current. So this is the Fleming's left-hand rule, the meaning. So if we think in such way, suppose you have this arrangement. North-south permanent magnet, and you have a conductor loop placed in the magnetic field, and the ends of the magnetic loop is connected to the slip ring and the carbon brush arrangement, and we are supplying an AC current. Suppose in this case you're in positive half cycle, so your current is flowing in this direction. Then, as per the Fleming's left-hand rule, you will have a force downwards. And this current, when it's passing to this side, it will return in this way. Then you will have a force upward, which will create a couple on this conductor loop, like that. So then this conductor will tends to rotate in anti-clockwise direction. So this is the basic phenomena of working of this AC motor. In next slide, we can see three-phase arrangement of such motor. See, there are three poles. Each are connected to separate phases, three phases. So suppose in this phase, if you supply positive half is going on, the current is come in from this end. That time your top part is creating, that time it was creating here the red. That means the north. And this time it is red, and this time it is north. When the supply alters its polarity, that time your magnetic polarity also changes. As there are three phases which are 120-degree electrically spaced in place, then there will be a rotating magnetic field as the supply given to these three poles. So there will be rotating magnetic field, which means the conductor which holds in this rotor, they are subjected under influence of rotating magnetic field, varying magnetic field. This varying magnetic field, which will induce some EMF in the rotor. then there will be some current flow inside the rotor. As the rotor start to flow some currents, then there will be another magnetic field which is induced in this rotor. That is the magnet that you can see north south. It is induced magnetic field due to this rotating magnetic field, influence of the rotating magnetic field of the stator. Now what will happen as this stator rotating magnetic field rotates, here in this south will attract the north part of the rotor. Again the south attract north here also. So which means this rotating magnetic field of the stator will always try to pull the rotor into that pole. So it's keep continuing, which allows the motor to rotate. But we have to keep in our mind, this rotating magnetic field, it has a speed. We call it synchronous speed, which is equal to 120 into the frequency, supply frequency divided by number of poles. So it has a synchronous speed. In this motor, normal induction motor, this rotor always drives at a slower speed with a slip. Normally it is about from 1% to 3% of slip. So always the rotor is driven at lesser speed than its synchronous or the rotating magnetic field speed. That's why we call these motors asynchronous motors. For synchronous motors, the rotor is driven at the same speed as its stator rotating magnetic field speed. So these are the very basic of a motor, how it rotates. So this session I will stop here, and then on next session we will start to discuss about the reactance, resistance of the motor, and how the motor changes its power factor while starting. It's taking a very large lagging power factor, but as the motor gains speed, the lagging power factor is improving. How this is going to happen? So these topics and the torque characteristic of the motor, how the rotor resistance is important to control the torque, and how we can assist starting torque of the motors. So what are the principles behind of these dual cage rotors and the wound rotors, these things. So gentlemen, thank you for being with me. So hope to see you again in next video. If you have any clarification or any comments, you can comment in below comment section. Thank you.